Hello. In this video, we are going to study about free body diagrams. Almost every mistake in engineering mechanics starts from a bad free body diagram. If you draw the forces wrong, the math will always give you the wrong answer. Now, by the end of this video, we will be able to work and create free body diagrams for situations like this. Now let's understand what a free body diagram is. So, a free body diagram is simply a diagram that shows all the external forces acting on an object. So it shows all external forces on an object. Notice that I mentioned external forces specifically because forces can also be internal. For example, nuclear forces or forces found within atoms. So we're only focused on the external forces. Now, before solving anything in mechanics, engineers first isolate the body and they draw all the forces acting on that body. That whole drawing is what they refer to as free body diagrams. For instance, in our situation right here, this and this, both of these blocks, represent two objects. When we isolate them and study them independently, and when we draw forces, external forces acting on each one, then you will be drawing the free body diagram. Now, the steps that engineers typically follow are that they isolate the objects. Then they replace the surrounding with forces. So they replace the surroundings with forces. And then they represent the forces as arrows. And this is done so we can understand the direction of those forces as well, since force is a vector quantity. Now, since we are only discussing the external forces acting on these objects, let's take a look at some external forces that we should be familiar with and the ones that we will come across in free body diagrams. Among these external forces are, first, weight, and then we have friction, then we have tension, and then we have the last one, normal reaction force. Let's take a look at each one first, starting with the weight. The weight is simply the force due to gravity. Any object placed on the surface of Earth experiences the Earth's gravitational force. And that gravitational force is determined using the formula W equals mg, where g represents the gravitational acceleration of the planet on which you are, which is Earth in this case. So g would be equal to 9.8 meters per second square, which is the gravitational acceleration of Earth. M represents the mass of the object. So say for example, you have an object that weighs 10 kilograms, then the weight of that person or object, well, not person, object would be 10 times 9.8, which would give you 98 Newton. And then we have friction. To put it simply, friction is just the force that opposes motion. It acts parallel to the surface and it opposes motion. Now, friction is represented by the formula F equals mu n. Now here you have two important terms. Mu represents the coefficient of friction, which is dependent on the surface on which the object has been placed, whereas capital N represents the normal force, which is the normal reaction force that we will get to in just a little bit. Now, the magnitude of this force, of this friction force, tells us how much opposition you have to the motion of an object. Then we have tension here. Tension corresponds to the force that occurs in strings, cables, or ropes. And a key property of tension is that it always pulls away from the object. And then finally, we have the normal reaction force. Now, the normal reaction force is the force exerted by a surface on which the object has been placed. Exerted by surface perpendicularly. So this is a force produced perpendicularly to the surface by the surface itself. Now that's all we need to know about the external forces. We have weight, friction, tension, and normal reaction force. Now let's take a look at how we can apply these forces and what we learned so far into a certain situation like the one we have here to draw a free body diagram. Let's imagine that this situation has an inclined surface, as can clearly be seen, of 30 degrees. And let's also imagine that both of these boxes, the one that is hanging freely and the one that is on the incline, both of them weigh 10 kilograms. So M2 is 10 kilograms and M1 is 10 kilograms as well. So the incline is 30 degrees. The masses of the two objects are 10 kilogram each. Now let's take a look at how you can draw the free body diagram here. There's a proper step-by-step methodology that you can follow, with the first step being isolating the object, as mentioned before. Isolating the object, which means that we are going to treat both of these boxes as two separate objects under the influence of different forces that are not related to one another. So you can either use the boxes as they are, or you could use just a simple dot like this or a point to make it easier to represent the whole diagram. Now, it's not necessary for you to only work on boxes. In real life situations, you'll get to deal with cars, you'll get to deal with cranes, you'll get to deal with a lot of other stuff that does not look like boxes or points. After isolation of the object, you have to identify all the interactions. Identify all interactions. Now, all interactions means all the different forces out of the four that we talked about acting on these two boxes separately. So for this, you need to ask yourself, let's start with box number 1, which is this one in this case. And this is box 2. So if we start with box 1, ask yourself, is gravity acting on this box? And as you can see, it has a mass, and since like every situation in engineering assumes that the objects are in um, Earth's atmosphere, then gravity is definitely going to be acting on the object as well. Now, gravity acts downwards, which means if this is how the object is placed on an incline, then the weight or the force of gravity will be like this. So this green arrow represents the weight. Now again, you need to ask yourself, is there contact with the surface? Now, as you can see, the box is placed on an inclined surface, so there is a clear contact with the surface. Among the four external forces we talked about, friction and the normal reaction force are both dependent on contact with the surface. Friction depends on whether the surface is rough or smooth, and depending on your situation, you may choose to ignore friction for certain scenarios. But normal reaction force will always be present. Now, normal reaction force, as discussed earlier, is exerted by the surface perpendicular to the surface itself. So the normal reaction force will be like this, acting perpendicular to the surface, like that. So the purple arrow represents the normal reaction force, and I'll represent it with a capital N. Besides that, if we assume that the surface is rough and that there is a friction here, then the friction will be represented by an arrow going in the upward direction, like this, since it's going to oppose the motion of this block. Now, the friction will be directed upwards if we assume that the block is heavy enough to slide downwards or to move downwards. In case the second mass, the block number 2, is heavier and it makes it so it pulls the block number 1, then friction could be directed in the opposite direction as well. So whatever the direction of the block is, friction will be in the opposite direction. And finally, we have tension. As discussed earlier, tension occurs in strings, cables, and ropes. We do have a string here which is extended and it's pulling on both of these blocks if we look at them separately. Now, we also discussed that this tension, this force, it's going to be pulling away from the object, which means in this scenario, it's going to be directed in this direction. So the orange arrow represents tension, represented by a capital T. And for friction, you can represent it with a small f next to its arrow, like that. So that takes care of all the interactions that this block number 1 is performing or like exposed to. Now, if we go to box number 2 or block number 2, it has its own forces as well. And again, you need to ask yourself, is it under the influence of gravity? Yes, it is. So you draw an arrow pointing downwards to represent its weight. Now, is it in contact with any surface? No, it's not. That means friction and normal reaction force are out of the playbook now, which leaves us with tension. So is there a string, extended string, attached to this block? Yes, there is. And since tension is a force that always pulls away from the object, then it's going to be directed upwards in the opposite direction of the weight. After successfully drawing the free body diagram with all the forces in their correct directions, you can then use the different formulas, like the formula of weight, the formula for friction, and then the laws of Newton to create equations that will help you identify any unknown force in this situation. If you want more videos like this, check out the link in the description. It will lead you to our website where you'll find multiple courses about engineering subjects, and you'll find other resources like worksheets and notes as well. Take care and have a good day.